my channel, and today I'm going to be talking about the history of physics. In this video specifically, I'm going to be talking about special relativity. Special relativity was published in the year 1905 and is created by one of the most famous physicists, namely Albert Einstein. Special relativity provides insight into time, light, and is essentially a different perspective of our universe itself. So special relativity is very important. To understand special relativity, we must look at two important facts. Namely, the speed of light is always constant, and the principle of relativity. So let's begin that the speed of light is always constant. Now that's a pretty obvious fact, but back then there was a lot of debate. So, why is the speed of light always constant very important to the theory of special relativity? Well, in classical mechanics, we can add and subtract speeds. We can add and subtract speeds. But when we have this example involving light, so let's first take the example with classical mechanics. So we'll call this classical. And we take a car and we have a person inside this car. And they throw a ball, let's just say 6 miles per hour. Now let's pick 4 miles per hour. And we also have another person who's just standing and is also throwing a ball at 4 miles per hour. Now notice that we have to count that the car is also moving, whereas in the stationary perspective, nothing's moving except the ball and the hand. So as you can see, the classical method states that we have to add the velocity or speed of the car itself to the speed when we throw the ball. So for example, let's just say it's going at 43 miles per hour. So we must take 43 miles per hour and add it to 4 miles per hour to get the total speed of the ball when thrown. So that's important because it's moving. If it's stationary, it's the same. But since the car is moving, we have to do this. Whereas it's just 4 miles per hour over here. So that's the big difference when we consider classical mechanics. But here comes the main difference about when we include light. When we include light, I'll just call this special. We can't add and subtract velocities of light. So for example, if a car is moving, let's just say 90 miles per hour, and a person in this car fires a beam of light from a flashlight, and a person stationary also takes a beam of light and flashes it. Then as you can see, the speed of the light is always going to be the same, even when the car is moving at 90 miles per hour. The speed of light is always constant, so we can't add and subtract speeds or velocities. So this is wrong when we're looking at special relativity, specifically at light. Okay, and this only works for light. If we have any other, for example, like a ball or anything, we still can add and subtract velocities, but when we consider light, we can't because it has a definite speed. That's why the speed of light, specifically, is always constant. Okay, now let's talk about the principle of relativity. The principle of relativity is pretty simple. So the principle of relativity states that if we take two objects, let's just say a ball, and let's just say we're in space, and then someone throws the ball in space. So the ball is moving at a velocity of, let's just say, 5 miles per hour. And then another person is here, and they're also in space. Okay, now, as you can see, the principle of relativity states that in this person's perspective, so we'll call this person, in the person's perspective, the ball is moving at 5 miles per hour. But in the ball's perspective, the person is moving at 5 miles per hour. And we can't justify which is right because we're saying that essentially we can't tell that if this person's moving or the ball is moving, because the ball, in that perspective, the person's moving. And then in the person's perspective, the ball is moving. So we have different perspectives and we can't really say which is moving and which is not. Of course, when we essentially define that we're following one person's perspective, we can say the other is moving, but in reality, we have two different perspectives. Okay. Now that we've talked about the principle of relativity, which states that we can't really justify or tell which object is moving relative to each other. So, as I mentioned, if we have a person and a ball, we can't really tell because one person has a different perspective, whereas the ball has another different perspective. So, as you can see, we have different perspectives, and we can't tell which is moving, only if we decide that we're going on one person's perspective. So, now that we've talked about the speed of light is always constant, which is the first important fact, and the principle of relativity, let's talk about frames of reference. Okay, so what's a frame of reference? Well, a frame of reference is essentially specific conditions or axes or coordinate systems which we're measuring an object relative to. So for example, if we take a car, and this car is moving, and we have a person sitting inside this car. So this person is sitting inside this car, and so since the person is sitting inside this car, then we can consider that the frame of reference is the car. But we can also consider a frame of reference in a different perspective. So another common example is if we have a box. If we have a box and a person inside it, as you can see, the frame of reference here is the box, because we're measuring the person relative to it. For example, we could even consider another box outside that box. And when we consider the other box outside of that box, we can also consider the person being relative to this box. But as you can see, it's different, because when we're considering the person relative to box number 1, which is the smaller box, then we're going to have different results. Whereas when we're considering to the second box, because we can take the person and jiggle, for example, or jump up and down in the second box. So it's going to be different when we take different frames of references. So again, we're talking about perspectives, different frames of references, where we're dealing with specific conditions or specific boundaries, and we're trying to analyze an object relative to specific boundaries or boundary conditions. So that's what a frame of reference is: specific boundaries, coordinate systems, axes, or specific conditions that we have, and we're measuring an object relative to it. Like it's over here, compared to specific boundaries or coordinate systems, and so on and so forth. So that's a frame of reference. Now let's talk about the inertial frame of reference. So the concept is the same when we have a frame of reference. The inertial frame of reference just states that when we take a frame of reference, if that frame of reference, for example a box, is stationary, then that's an inertial frame of reference. On the other hand, if it's accelerating, it's not an inertial frame of reference. But if it's at constant velocity, meaning that the second derivative essentially is 0, which means constant velocity means the acceleration is 0, which means the second derivative of the position function is essentially 0, because the first derivative is velocity, then we can essentially state that the second derivative of the position function is 0, which means we have constant velocity. So when the acceleration is 0, then the object can stay at rest, or it can move at constant velocity. So if the frame of reference is moving at constant velocity or is at 0, we consider that an inertial frame of reference. Now that we've talked about what an inertial frame of reference is, let's talk about E equals mc squared, perhaps one of the most famous equations of all time. E equals mc squared, along with F is equal to ma, but that's in classical mechanics. E equals mc squared is one of the most famous equations. E equals mc squared just states that energy and mass are directly proportional to each other. So energy is equal to mass times the speed of light squared. And this is pretty obvious. But this isn't the full equation. I've also made another video talking about how there's another equation, which I'm going to talk about right now in more detail. But to say right now over here, E equals mc squared is not the full complete equation. E equals mc squared is essentially just stating the energy when an object is at rest. Okay, so that's what E equals mc squared states. So instead of saying energy is equal to mass times the speed of light squared, which is too vague because energy means the total energy, and if an object is moving, it gains some energy. So essentially, we can't really say it. So this is wrong. Pretty much, energy is equal to mass times the speed of light squared, is pretty much wrong when considering all energy, but only considering a specific case when the object is at rest, it's precisely correct. So how do we get this? Well, E squared equals mc squared squared plus pc squared is another equation. It's not deeply into special relativity. It's not a concept, but it's also very important. Okay, E squared equals mc squared squared plus pc squared, where P, we already know that m is mass, c is the speed of light, E is energy, P is the momentum. Okay. Now, let's just say that we're going to derive E equals mc squared from this equation, because we're stating that E equals mc squared is when the object we're measuring is at rest. If the object is not at rest, then we're using this equation, but which means that we can derive E equals mc squared from this equation, so we have to test it if we can derive the proper equation when an object is at rest, namely E equals mc squared. So how do we derive E equals mc squared from this? And that's the main question. Well, if we set the momentum equal to 0, that means this term cancels off. Simplifying, these cancel, so we have E equals mc squared. Pretty much that's how we get it, when the momentum is 0. And this proves that when the momentum is 0, that means the object is stationary, which also follows the specific conditions of E equals mc squared. What about when the mass is 0? When the mass is 0, this term cancels out. So we just have pc squared. Canceling out, E is equal to pc. So E is equal to pc is when the mass is 0. So E, the energy, when the mass is 0, is totally dependent on the momentum and the speed of light. Okay. Now that we've talked about that, and the specific equation for E equals mc squared, or the more general term or equation, let's talk about time dilation. So there are other specific things, like there's a formula for time dilation, but since we're talking about the history of physics, we're not going to dive deep into the specific mathematics. But time dilation is essentially specifically pretty mind-boggling when we consider this. So say we have Earth, which we'll abbreviate E. And so on planet E, or planet Earth, we have a person on it. So this person has a clock. And this clock is ticking at the regular rate and synchronized to the other clock. But when this clock is moving out in space, in a rocket, and it moves faster and faster and faster and faster, the person over here sees that essentially their clock ticks slower than this clock over here. So the person on planet Earth, their clock ticks faster, whereas the person on the rocket ship, their clock ticks slower. Since they're going faster and faster, whereas the person on the Earth is just on Earth. So when you're going faster, essentially, time slows down for you. And that's essentially what time dilation says. So time dilation is a pretty cool concept. And we have many other concepts in special relativity, like length contraction and so on and so forth, but we're not going to be talking about today, as we just gave a brief overview of what special relativity is. So let's summarize. So here are the two important facts. The speed of light is always constant, and this is specifically for light, because usually when we consider classical mechanics and any other objects, we can add and subtract velocities. However, this doesn't work when we just consider light. And then we have the principle of relativity. Oh, and by the way, the speed of light is always constant, means that we can't add and subtract velocities when we have light. So speed of light is always constant. The principle of relativity states that when we observe, so when we have two observers, one observer's perspective states that the other observer is moving towards them, and the other observer's perspective says that the other observer is moving toward them. So we can't really say which observer is moving. So it depends on which perspective we actually choose. So that's the principle of relativity. We can't really justify or say which observer is actually moving, because they both have different perspectives. Okay, next we have the frame of reference. The frame of reference is essentially, or frames of reference, is essentially just when we have specific boundary conditions, or a specific place or specific area, or specific coordinate systems, axes, or whatever, when we have specific a reference frame, and where we can measure an object relative to a specific boundary, condition, coordinate systems, or so on and so forth, that's a frame of reference. For example, as I mentioned, when we have a box, the box is a frame of reference because we're measuring the person relative to the box, we're not measuring the person relative to the road, or we're not measuring the person relative to the car, which the box is in. So essentially, as you can see, the frame of reference is essentially where we're picking to measure the object that we're measuring relative to. So we can pick different frames of reference and get different results, even though the total result is the same. Well, the total result is the same, but since we have different perspectives, it's going to be different. Because the frames of reference states that when we have two different frames of references, we're obviously going to get different answers because we're measuring them relative to different things. So frame of reference is when we're taking a specific boundary condition or a specific boundary or coordinate system on axes and measuring an object relative to that specific boundary. Okay, so that's essentially what a frame of reference is. An inertial frame of reference is the same as a frame of reference, but it's essentially when the frame of reference is at rest, so it's not even moving, or when the frame of reference is moving at constant velocity, which means that the acceleration is 0. Last but not least, we have E equals mc squared, which is essentially talking about the energy when an object is stationary. And then we have the other equation, which is particularly the general form. E squared equals mc squared squared plus bc squared, and we can derive E equals mc squared from that. And then time dilation, which states that when you move faster, then time slows down for you compared to people on Earth. Okay. Now that we've talked about that, we can make this video to an end. If you like this video and if you like this channel, please subscribe to learn more. Thank you.